Good morning, everyone. Today I'm excited to introduce Dr. Chloe Whicker-Clarke, who's a researcher at UCI and who has recently been supported for the last year by E3SM and the SciDAC Fancy project jointly to help E3SM simulations of ice sheet mass balance. Before that, she completed her graduate studies with Mark Flanner at the University of Michigan, where she was supported by the NSF Graduate Student Fellowship Program. Her thesis work on bare ice reflectance was an innovative application of Mie scattering theory to air bubbles in solid ice that led to one of the improvements in E3SM simulated surface mass balance that she will mention in her talk. You can learn more about the subjects that she will describe at one of the two sessions she is co-chairing at AGU this year on Monday and Tuesday mornings. So I have nothing more to add. Chloe, go ahead and start anytime.
So thank you again for the introduction. Like Charlie said, this work is funded by Fancy and E3SM, where Fancy is the framework for Antarctic system science in E3SM. So today, I just first want to thank those of you who have allowed me to give this presentation today, and then everyone who is here to listen. So the presentation today will be on ice sheet surface mass balance in E3SM and the validation to the model. So starting off with just a little bit of background, the melt of glaciers and ice sheets or land ice contributes approximately 1.2 or 1.5 to 2 millimeters per year of sea level rise. So we can see that here, these gray regions are land ice. And we can see that those contributions have been increasing since the early 1980s. And we expect those contributions to continue to increase under increasing polar temperatures. However, sea level rise projections remain uncertain due not only to uncertainty in different emission scenarios that we will take. So, for example, the red and the blue are two different emission scenarios, but also due to challenges in modeling glaciers and ice sheets. So, for example, the spread within these projections sort of highlights some of the uncertainty that part of which stems from uncertainty in modeling glaciers and ice sheets. So zooming in specifically on just ice sheets, the Greenland ice sheet and Antarctic ice sheet have significantly contributed to sea level since the early 2000s. So shown here, we see the Greenland ice sheet contribution to sea level in blue, and then different parts of Antarctica in pink, red, and yellow. So this really highlights that accurate Earth system models simulations of ice sheet mass balance is pretty critical to simulating future sea levels. However, like I said, ice sheets are challenging to model, and there's still some uncertainty in modeling techniques. And that's because ice sheets are really complex structures. They have interactions with the atmosphere and land and ocean. So we have precipitation coming from the surface, and then we have interactions with the ocean, and then runoff on the land. So all of these processes are occurring. And then there are also processes occurring on both micro and macro scales. So for example, when we think about the microphysical processes of snow and ice, like the snow grain evolution as it ages and darkens. That's happening on a micro scale, as opposed to things like large calving events where ice is dropping off in large swaths into the ocean. So that would be considered a macro scale process. So it's important to consider all of these different spatial and temporal interactions and processes that are occurring when simulating ice sheets. So because the Greenland ice sheet has had such large contributions historically, we're going to zoom in and focus on the Greenland ice sheet for a second. So we can separate out the total contributions from the Greenland ice sheet in blue into both the surface processes and dynamics processes of mass loss, where surface is in this more green shade and then dynamics are here. So we can see that the surface mass loss has been increasing, especially since the around 2010. And so we'll define the surface mass balance just as the change of mass in the ice sheet just on the surface of the ice sheet. So we see mass coming in through accumulation, through snowfall, and then we see mass going out through melting and runoff and sublimation limited to the surface of the ice sheet. And so this graphic on the right shows, so the surface mass balance is strongly impacted by strong positive feedbacks. For example, the albedo feedback and the snow line elevation feedback. Both of those are shown in this graphic on the right. So as we see the winter snowpack melt off, we're seeing the fresh snow age and start to darken. And then we see the snow line elevation increase up the ice sheet and sort of show melt ponds and bare ice beneath, both of which are much darker than the snow. So now to just sort of put all of that background in the context of the projects I've been working on. So E3SM and FANCY have a goal of improving our ability to accurately simulate and project the state of ice sheets. So my aspect of this work is number one, it's bolded. We're working on improving the surface mass balance and energy budgets simulated specifically by the land model ELM, shown here in pink. We have that surface mass balance is then going to be passed to the MOLI, the glacier ice sheet model. And so we're also working on improving the coupling between the land model and the ice sheet model. And then yet another project is working on improving the coupling between the glacier model and the MPAS ocean model and the MPAS sea ice model. So all of the areas we're working on improved coupling are indicated in red. And then this project has also worked on slightly improving the coupling between ELM and the atmosphere, because like I said, the surface mass balance is strongly modulated by the incoming precipitation. And so it's really important to have accurate precipitation fields to simulate surface mass balance. So we're going to do a quick sort of sneak peek into our results of surface mass balance in ELM. And so we can see comparing ELM to a regional model, RACMO, which we'll talk about a bit more in a second. ELM compares really well to RACMO, both on the Greenland ice sheet on the left and on the Antarctic ice sheet on the right. And so we can see that ELM simulates the spatial patterns in surface mass balance quite well, and it overall simulates it within 5 or 6% depending on the ice sheet. And so the reason we are comparing to RACMO, which is the regional atmospheric climate model, is because it's a state-of-the-art regional climate model. It is really well evaluated against observations and has been developed specifically to simulate Greenland and Antarctic ice sheets. It's currently one of the best available comparisons we have for validating the surface mass balance, because surface mass balance is not directly observed through satellite observations, and we don't have ice sheet scale observations of surface mass balance. One downside to these regional models is they really only simulate historical and present day conditions because they are not fully coupled, and so they can't really operate in a projection way that E3SM can. So now sort of just moving on to our progress over the last 4 to 5 years. This is just showing the progression in our ability to simulate surface mass balance over the Greenland ice sheet in E3SM. So here we see the ELM Greenland ice sheet surface mass balance. Note the opposite color scale here. This was back from 2020, and so just as of last year, we really had improved that. We had gotten improved resolution, better accumulation. And then as of this year, we see much better, much higher resolution, much more accurate looking ablation and accumulation patterns. So not only do we have a much improved surface mass balance product over the Greenland ice sheet, but we have also worked on developing tools that allow us to compare that with regional models, allow us to compare it with observations. And we've been working, as I said, on the coupling between ELM and MOLI simulations, the glacier ice sheet model. And so to actually simulate the cumulative mass change over the ice sheets. So how did we get here? What progress have we made and what is left to be done? So we have sort of taken a three-pronged approach to improving our ability to simulate surface mass balance. And the first is improving the representation of snow and ice physical processes. So that will include work like our new and improved snow and firn densification model. And also that'll include work that we're actively working on, such as the formation of melt ponds and ice lenses. The second prong is improving the radiative properties of snow and ice. So we've worked on incorporating a more advanced representation of bare ice albedo within ELM, and then also have incorporated an improved snow thermal conductivity within the snow densification model. In the future, we hope to improve the refrozen snow grain size representation to do a better job at capturing the snow albedo feedback. And then from the atmosphere side of things, we also have have introduced a new data atmosphere forcing, ERA5, that has a more realistic snow accumulation rate than other options. And in the future, we hope to improve our downscaling of atmospheric drivers to ice sheet elevations to improve our temperature and precipitation rates over the ice sheet. So now we'll just work through sort of each of those bullet points that I've discussed, starting off with the ERA5 data atmosphere forcing. So we chose ERA5 because the precipitation closely matches accumulation data from shallow ice cores over both the Greenland ice sheet and Antarctic ice sheet as seen here. So here we're comparing ERA5 precipitation to CRU-NCIP precipitation compared to the Greenland ice sheet and Antarctic ice sheet accumulation. And we can see that ERA5 has much higher correlation than CRU-NCIP. And we can see sort of the same thing here, where ERA5's correlation is much higher than that of CRU-NCIP over the Greenland ice sheet. So this new atmospheric data set is available for use on Perlmutter with a tested comp set. So if you are interested in using that, feel free to reach out. So what we've done with this new data atmosphere is we ran a 1,000-year spin up to develop a 1980s climatology and fully spun up snowpack model using our new snowpack model that we have implemented. So this new snowpack model includes a much deeper snowpack. So we've transitioned from the traditional 1 meter snowpack in Elm to now a 30-meter snowpack, which if we look here, where this is our new 30-meter snowpack, and this is the original 1 meter snowpack, we can see that we have a much deeper snowpack over the ice sheets, which is really important for accurately simulating surface mass balance and understanding the ice sheet's ability to respond to high emission scenarios or tipping points in the climate system. So with this new deep snowpack, we're able to simulate snow, and then as it compacts into coarse-grained snow and then burn, which is essentially just much denser snow that has been on the ice sheet for multiple seasons. So we're able to simulate that transition, and we're also able to more accurately simulate the density as a function of depth. So here we're comparing E3SM to observations, empirical models, and CESM, and we can see that this new snow density model compares to observations much better. And so this work is currently being prepped for fully coupled simulations and tests, and should be available. We also have improved the bare ice albedo scheme within Elm. So historically, Elm has utilized a constant bare ice albedo, shown here in this middle plot. But in reality, bare ice albedo is highly variable. As shown, this is the MODIS summertime average bare albedo. And so what we did is we implemented a new ice radiative transfer model. It calculates the albedo based on the physical properties of the ice and the atmospheric conditions. We see that using the MODIS-informed bare ice properties, we see much better agreement and much more variability as shown here. So some future work on this topic is to develop a MODIS-era climatology of the bare ice properties to utilize in different periods and regions, because this study was specifically limited to the Greenland ice sheet during the MODIS era. So we've also worked on improving the snow thermal conductivity in Elm. So historically, the snow thermal conductivity relied exclusively on snow density, which is shown here in this black dashed line. So that was the implementation that has been in the model for a while and was developed by Jordan et al. In 1991. So this new proposed implementation was developed by Fortreau in 2021, and we see much more variability because it relies on both snow density and temperature, as shown. So some future work includes including this modification in longer simulations of surface mass and surface energy budgets to understand its impact on the total ice sheet mass balance. And so while we have made all of these improvements to the model physics, we also have been working on ways to quantify those improvements. And so we've been working with the E3SM infrastructure group, specifically Michael Kelleher, working on utilizing and extending the previously developed LiveKit tool. So LiveKit is the Land Ice Verification and Validation Toolkit. It generates publication quality plots of surface mass balance and surface energy budget variables. It also intercompares models and evaluates them against available observations and reanalysis data. However, LiveKit is currently limited to the Greenland ice sheet, But some future work we hope and plan to do is extending this analysis to also be over the Antarctic ice sheet, and then potentially even working with the infrastructure group to incorporate it in the Zippy architecture to allow many more users to access this kind of comparison. So I just want to highlight that we're shifting into results, and I just want to highlight that most of the plots I'm going to show are actually generated from the LiveKit toolkit. So starting off with the ELM surface mass balance, we saw this plot before, but I just want to dig into it a little bit deeper and sort of highlight what we can learn from it. So we know that ELM is able to simulate the Greenland ice sheet surface mass balance well within about 5% of this regional model. However, we are missing ablation in northern Greenland, as you can see here in the contrast between ELM and RACMO on the left and right, and then also in the difference plot here on the edge. So we can see that we're missing a lot of ablation, especially in the northern ablation zone, and then also to some degree in the southwest ablation zone. So this underestimation of ablation is actually resulting in about a 15 kilograms per meter squared too high of surface mass balance. So if we look at that from the perspective of the seasonal cycle, comparing RACMO's seasonal cycle here to ELM's seasonal cycle here, we can see where surface mass balance is in black, and then other surface mass balance related variables such as precipitation, refreeze, runoff, those are in other colors. We can see that we achieve a similar surface mass balance as RACMO, but we don't achieve nearly as much variability. And it looks like most of that can be attributed to not achieving enough variability in snowmelt or runoff. So I think these things are things that we hope to improve by improving our wet aged snow albedo scheme, and also by improving the downscaling of precipitation and temperature to glacier elevations. Because what happens is ELM receives the atmospheric variables from the atmosphere model, and then over the ice sheets, it further downscales that atmospheric forcing to various elevations, because glaciers and ice sheets are so sensitive to changes in elevation. So for example, we could expect to see more precipitation as rain over low elevations and higher temperatures over low elevations, and that may improve our ablation in the low elevation ablation zones. So still looking at surface mass balance, but now compared to observational data sets. This is sort of telling the same story that we saw in the comparisons with RACMO, where we see that ELM is really able to capture the surface mass balance trends and magnitude in the central Greenland ice sheet and also in the southwest ablation zone. But we fail to capture the ablation in the northern and eastern ablation zones. And so we can see this when comparing to observations, as well as looking at correlation plots between ELM and core observations and promise observations between accumulation and ablation. So here, again, we can see that the accumulation representation is really good, and a lot of that is probably due to our ERA 5 data atmosphere forcing. But we do see that we just are unable to capture a lot of ablation. So another way to look at this is to look at the surface energy budget. Or to look at the albedo. So here we're comparing the ELM albedo to both RACMO 2.4 and series reanalysis data. So compared to RACMO 2.4, the RACMO albedo is actually about 2% higher than ELM and about 5% higher than series. So ELM is actually doing a pretty good job at simulating surface albedo. However, when comparing to series, we do see that ELM is failing to simulate the low albedo in the northern ablation zone and around some of the terminal edges. I think it is worth noting here, though, that the surface energy balance analysis is still in a pretty preliminary state. So we do want to further refine the comparison against series, because series has very low low resolution. The resolution is about 1 degree by 1 degree. So we could be theoretically getting bare ground or maybe even ocean albedos averaged in here. So this could be a potentially too high of bias than what we're actually seeing in reality. So these are just preliminary results. So now sort of shifting gears, what we're doing with this surface mass balance. We can take the surface mass balance that we're simulating in ELM and use it in a coupled state with MAHLI, our glacier ice sheet model. We can simulate the entire ice sheet mass change instead of just the surface mass balance. So let me preface this with this work is still in progress, but I just want to highlight that we're making really good progress on our coupled side of things. So this is a plot that I showed back at the beginning of the talk, where we're looking at the Greenland ice sheet observations, mass balance in blue, and then we have overlaid our new coupled Elm-Molly simulations, where we're working on different techniques, for example, testing different linear sliding techniques or different calving techniques to accurately reproduce the cumulative mass change over the Greenland ice sheet. And you can see that through our iterations, we've made substantial improvements. For example, this was a previous iteration, and now we're getting much closer to these observations. And it's worth highlighting that that potential surface mass balance high bias that I discussed a couple slides ago, it's worth highlighting that some of this high bias in our total mass trend could be attributed to the surface mass balance. So this is still a work in progress, and we are still working on improving it. I just want to highlight that we've made great progress so far. And now shifting gears to the Antarctic ice sheet. So ELM is able to simulate the Antarctic ice sheet surface mass balance within about 6% of RACMO, which I showed at the beginning. And we see that ELM is accurately simulating spatial trends in surface mass balance quite well, where we have ELM, RACMO, and then the difference. It looks like, conversely, to the Greenland ice sheet, which was high biased, it looks like the Antarctic ice sheet is slightly low biased compared to RACMO. It's going to require some further analysis to attribute exactly where this low bias is coming from, although some other studies have potentially attributed it to possibly missing blowing snow off of ocean grid cells, so we're not fully capturing all of the accumulation. So the Antarctic ice sheet surface mass balance is particularly important to some of the goals of this work, because we want to work on improving capturing our ability to capture tipping points under future emission scenarios. So to accurately simulate those types of things, it's really important to be able to simulate the microphysical processes happening on the ice sheet. So for example, one example of a tipping point that we would like to be able to capture on the Antarctic ice sheet is like large hydrofracture events. So one example of that would be on the Larsen ice shelf, where we started to see accumulated melt ponds on the surface of the ice sheet. And then within a couple of days, the ice shelf collapsed into the ocean, which then led to rapid collapse and then acceleration of inland ice flow. And so one of the methods that we think caused this collapse of the ice shelf is through hydrofracture. So essentially what happens is we get the percolation of liquid water down into the snow column. That liquid water then refreezes and starts to sort of drive a wedge into the ice sheet and make it less and less stable. So to accurately simulate a process like hydrofracture, we would need to be able to simulate complex physical processes, such as snow and ice melt and slush and melt ponds all accumulating on the surface. And we need to accurately be able to simulate the percolation and refreezing of liquid water within the snow column. And then we also need to simulate the radiatively active surface water because that triggers the snow albedo feedback. So all of these processes are really important to be able to accurately capture within the model to simulate these large-scale tipping point events on the Antarctic ice sheet. So our results on the Antarctic ice sheet are still preliminary, but I'm introducing some preliminary analysis of the snow properties that could potentially be useful for analyzing to better understand our sensitivity under high emission scenarios and the robustness essentially against large tipping points. So here we're looking at the Antarctic ice sheet on the left. We're looking at the Antarctic ice sheet firn air content spatially. So this is the amount of air held in the snow and firn column in the top 10 meters of snow. And so this information is particularly useful because if we see really low firn air content, that means if water is percolating down the ice or the snow column, then we're losing pore space and potentially destabilizing the ice sheet because we're introducing these ice lenses and potentially wedges into our ice sheet. So again, this is preliminary results, but now if we look at sort of this spot on the Larsen ice shelf, we can look at the density, firn air content, and liquid water mass now with depth. So I chose a spot that is particularly interesting because we see sort of a spike in the liquid water mass in the second layer of the snowpack. And so that spike in liquid water mass leads to a rapid drop in our firn air content and a rapid increase in our density. And so this is a good example of something where we could sort of trigger, this would allow us to understand like, oh, there's probably an ice lens here, which and an ice lens is essentially when we get a slab of solid ice in between two snow layers, which doesn't allow for liquid percolation down into the ice sheet. So this is one example of a potential analysis that we can perform with these new and improved snowpack modeling and our new snow diagnostic fields that we've introduced into the model. So lastly, I'll just sort of go over a quick summary of everything I've presented today. So we have done a lot of improved science within the E3SM model. We've improved the representation of surface mass balance using new snow physics, a new snow and ice routing and densification scheme, and also we've improved the coupling to the ice sheet model Molly. We've also improved the surface mass and surface energy balance fields within ELM and added new diagnostic fields to analyze those processes. And we've also improved the data atmosphere forcing options and grid resolution. So all of these improved science topics have come with new model developments, such as our snow and firn compaction scheme, our new ice albedo radiated transfer scheme, the improved snow thermal conductivity, and then work that's still in progress is improving the snow grain size and the formation of melt ponds lenses. So I'm gonna do this so I everyone again, and I'll leave this slide here and take any questions.